Predicting weather through numerical analysis. This is for Computer Science 440 numerical analysis at the University of Nebraska-Lincoln, and this is our team. So here's our motivation and our goals. First off, the motivation was to accurately predict the weather through decision making, whether that be through agriculture, transportation, or disaster management, and how we can use that maybe in the future for this project. Additionally, the goal was to leverage these numerical methods and estimate the weather conditions effectively using our data points. We'll explain a little bit later about how that data worked and what that looked like. And finally, the objective was just to implement and compare these interpolation techniques and model these temperature trends over a given period of time. In this case, it was for over the course of a year.
So for our data sources, we chose to use the information from weather.gov. We picked the high temperatures for the day from October of 2023 to September of 2024. We then collected that data, put it in an Excel sheet, and then put them into comma-separated lists so we could put them as arrays. We then use those arrays to plug them into our algorithms and simulate and plot the data through numerical analysis. So the implementation methods we chose to use were linear interpolation, a simple yet effective method for estimating unknown data points; cubic spline, a smooth technique to better fit the volatile weather data with piecewise; and R-cubic spline, very similar to cubic spline, just tends to be more efficient and effective at handling different changes. Now on to implementation.
So, challenges and solutions. One of the first challenges we had was sharp weather transitions, like when there's a 20-degree drop, for example, day to day. And the solution for this was using rational cubic splines or piecewise defined functions, which allowed us to handle those discontinuities and smooth it out. Another challenge we face specifically with weather data is big outliers. As we know, weather isn't always the most predictable, and we've had some really hot days like a 90-degree day in October or really cold days in hot seasons. So how we dealt with that was using adaptive splines that minimize the impact of these extreme outliers. And finally, to select the best method out of these three, we used the mean squared error method to compare how well these methods did against each other. So results. These are the original temperature data points from Lincoln, and next we have the original temperature points from LA. So at 10%, you can see it follows the trend pretty well, and as you go on to 50%, less of the data is captured, and then at 80%, even less is captured except the general trend. And now when you go on to LA, you can see the range of temperatures is a lot smaller because LA is a coastal city and the climate doesn't vary as much. At 10%, it follows the trend pretty well. And similar to Lincoln, at 50%, doesn't follow it as well. And then at 80%, it misses a lot of data points.
So in Lincoln, for the cubic spline method, here at 10%, it's pretty accurate, but you see it misses some points. Moving on to 50% for the cubic spline, we're missing quite a bit more points, but it's still following the trend well. On 80%, it misses a majority of the points, but you see it catches some of the highs, some of the lows, and follows the overall trend. You can see at the end, towards the end of September, it skyrockets way up over 120. This is an incorrect value, but it just comes from the trend of the data towards the end. It's trending up sharply, so the cubic slime interpolates that to be upwards towards 120. In Los Angeles, the more predictable weather performed a little better. Here at 10%, it's fairly accurate, but you see another outlier there at the beginning in October where it shoots way down below 40. That's just because of the trend of the data in that region. Move on to 50%. 80%, we're going to be a little less accurate, but still following that overall trend using cubic spline.
Onto our cubic spline. For the first one, with the way our cubic spline works, we're moving 10% of the data. You need a step size of 1. So this is actually still all the data. So every point is hit with the R cubic spline at 10% damage. Moving on to 50%. This has a step size of 2. So every other point here. It followed the data pretty well. As you can see, in January, it hit that outlier pretty low. It also just follows the trend overall, does a good job at following the weather. Now on to 80%. It's still hitting that outlier down low when it was negative for a week in January. And overall, despite missing 80% of the data, it follows the trend very well and can pretty accurately guess the weather. Onto Los Angeles, the more consistent coastal weather. As you can see, again, step size of 1, so every single point is hit here. 50%, it still does a pretty good job at tracking the data, especially in the really consistent stretch from December to May. It doesn't quite catch the outlier where it was 112 mid-August, but it goes up there and generally follows the scheme pretty well. And then finally, the lack of 80% of the data. It still follows the weather well, even better than what it did in the 50% even, just because it missing some of the outliers actually helped the data stay more closer to the mean, and there's no over/underestimating. Overall, it did a pretty good job at following the trends.
Now that we've looked at all the algorithms, we can compare the accuracy of each of them. This table shows the mean square error for each algorithm at each distortion level in both cities. This table shows the average of 5 trials for each entry. And a couple things to note. First of all, our cubic spline has 0% error at the 10% damage sample. That's because due to the step size, it's hitting all the same points as the original data. We can also see that the error is not necessarily correlated to the amount of damage, and that's because of the outliers. They have a huge impact on the accuracy of the interpolation. And in addition, we can also see that the LA values are generally more accurate than the Lincoln ones due to LA's more consistent weather. Now, to summarize our results, we found that linear interpolation is much less reliable with a volatile data set, such as weather, and we found that the spline methods were much more accurate at interpolating these. We also found that Los Angeles's more consistent weather patterns made it easier to predict and interpolate, and we found that more damage to the data is not directly correlated to less accuracy due to the effect that the outliers have.
So just to conclude, our recommendations to our boss that we can make is that the R cubic spline method demonstrated the most superior performance. As we kind of saw from that mean square error table, we saw that the least error was actually coming from this R cubic spline method. So this could be used for more accurate interpolations of the weather data for future events or anything that we might want to look at in the future. Especially when we're looking at these future work and what we might take into consideration if we were to continue on this project, is looking at real-time weather data and how we can incorporate that in to get more enhanced predictions, maybe more accurate predictions when it comes to, looking ahead, maybe 7 days in advance, 14 days in advance, whatever that might be. Additionally, maybe look at some more interpolation methods. If there's some method that works a little bit better for more complex scenarios or areas of high validity or volatility, that's, really hot summers or very cold winters. What does that look like depending, how close you are to the equator and maybe having more consistent data, or, like we compared Los Angeles to Lincoln, maybe more consistent data on the coast versus in the middle of the country. And finally, investigating machine learning models and how does that work for advanced analysis, getting more accurate data, maybe using the lows from throughout the week, or maybe taking the data from the morning, middle of the day, and the end of the day, and see how we can get more accurate predictions. Thank you. That's all we have.
Thank you.
Thank you.
Thank you.